Natural convection is one of the most frustrating topics in the entire heat transfer course. And that's really saying something because this is one of the hardest courses you'll take in your entire college career. And the reason for this is that every textbook you check is going to have a different equation for natural convection. And the reason is that every textbook you check is going to have a different equation for natural convection. And so your first thought might be, well, how do I know which one's right? And the answer is that actually all of them are wrong. Convection is so complicated, we do not come up with equations derived from first principles. Instead, we run hundreds or thousands of experiments and try to fit a curve to the data. And anybody can come up with any curve that fits data, sort of, sometimes. I mean, not to mention that experiments themselves are not perfectly accurate. So what I want you to learn in this problem is when you compare a vertical surface versus a horizontal surface with the hot side up or horizontal with the hot side down, just how do these three situations compare against each other? Like, which one has the most convection and which one has the least? And then I also want you to start to get comfortable embracing the ambiguity of convection, the ability to recognize that you will get different answers using different equations from different textbooks, and they'll be off by a lot, like 25%. And that's okay. Just pick one and kind of try to justify your choice as best you can and go with it. And if it's a homework problem, that's going to be fine. And if you're working out in industry, you may be able to use this as a first rough estimate and then maybe set up your own experiment to actually get data that's even better for your very specific case. So let's start off by grabbing some of the numbers out of tables that we're going to need in the back so that once we do get to the equations, we're just going to be able to plug everything in just super quick and easy. So first thing is going to be the Rayleigh number, which in many ways is used like the Reynolds number. You use the Reynolds number when you have, say, flow through a pipe or like aerodynamics, flow over a surface. The Rayleigh number is similar to that, but used for natural convection. The first part of this, like the big fraction, is another number called the Grashof number. You may recognize that name if you've taken a mechanisms course before, right? The Grashof criterion for a 4-bar linkage, whether it will actually rotate. Yeah, same guy. Basically, in the old days, there weren't actually that many engineers or scientists, so they kind of had to do everything. So nowadays, this is why like everything in all of your textbooks is named after like the same 20 people. So the Grashof number is essentially a ratio of buoyancy versus viscosity, because the driving force for natural convection is like hot air rises, right? When things are more buoyant, less dense, they rise. That is what causes natural convection. And so that's why the numerator is based on like gravity and L cubed is volume, right? So this is buoyancy in the numerator and the denominator viscosity. So how much buoyancy force is pushing up versus viscosity kind of holding it down. And then to create the Rayleigh number, you multiply by the Prandtl number. And this Prandtl number, which you'll remember from earlier in the course, is sort of a ratio between momentum and temperature. So for air touching a surface, there's sort of two main ways that heat gets from the surface out to the bulk air. Part of it is just like conduction through the air itself, just heat going from one air molecule to the next. And then the other part is the actual air molecules moving. If you have a hot air molecule touching the wall and it moves, right, that's how it can also take heat out. And so that is sort of the momentum portion. Prandtl number has to do with both the temperature effects and the momentum effects. So the Rayleigh number combines all of this: buoyancy, momentum, temperature conduction, and viscosity, kind of all into one. So that's why it really encapsulates natural convection. When we do go back to the tables to look up temperatures, everything's going to be at the film temperature. So this is the average between the surface temperature and the bulk temperature. So for this problem, 55 degrees and 25 degrees, we'll average those together. We're going to look up all of our properties at a temperature of 40 degrees Celsius. And the first one of these that we're going to look up coefficient of thermal expansion, which is actually just 1 divided by the film temperature, so I don't need to look that up at all, 0.003195. This equation only works for an ideal gas, and any chemists out there might be thinking, well, actually, air is not an ideal gas. Nerd glasses. Well, for engineers, air is an ideal gas. We like to make approximations, and there's going to be so many estimates in this problem anyway. You can definitely assume that air will behave as an ideal gas. Okay, but now to actually look up the numbers that we need, for viscosity, I always forget, is it dynamic viscosity or kinematic viscosity? You almost always want the one with meters squared per second, so that's the one that I'm using, the Greek letter nu, 1.7 times 10 to the negative 5th. And for the Prandtl number, at our film temperature, I'm grabbing 0.706, and the Prandtl number is unitless. Within the Rayleigh number, you'll see that there's an L cubed term. That is going to be the characteristic length. And this is actually going to be different based on the configuration of your system. So for a vertical plate, the characteristic length is the height, right? Hot air rises. So all of the air that leaves from the bottom of the system has to rise up to the top along the wall. You need to know the height. But for a horizontal plate, the air is just leaving the surface kind of everywhere. So in this case, your characteristic length is going to be area divided by perimeter. And for a square or a circle, this will end up being like the length divided by 4 or diameter divided by 4, which essentially is like the hydraulic radius you may have seen in your fluid mechanics class. So 0.6 characteristic length for the vertical surface, 0.15 characteristic length for the horizontal surfaces. Plug in numbers into the Rayleigh number, and we can get for case A, the vertical plate, this is going to be 4.96 times 10 to the 8 is the Rayleigh number for the vertical plate. And because there's a different characteristic length, the Rayleigh number is different for the horizontal surfaces, although they're the same as each other. 7.75 times 10 to the 6. So because the length gets cubed, this ends up being like 100 times smaller, not just like 4 times smaller. Now we should be able to jump into the problems, and once we find the equations, I think we'll have everything we need to just kind of plug in and boom, boom, boom. So natural convection is still convection. So we're still just using regular Newton's law of cooling. Q dot is HA delta T. We've got our delta T of 30 degrees. We've got the surface area, 0.6 squared. We just need to find H. And actually, in most textbooks, you won't find H directly. You're actually going to find the Nusselt number, NU. And the Nusselt number is defined as H L over K, which we can rearrange so that the value H will be the Nusselt number we'll find times K divided by L. And K, again, we can look up in the back, get 0.0273. The characteristic length here, 0.6. So just need to find Nusselt number, and then we'll get rate of heat transfer. So the first equation that I'm going to use is the one that's in the FE reference manual, which is kind of a clue that it's the easiest one, but also maybe the least accurate one. I'm also grabbing the version that's from the Sengel textbook here. C times Rayleigh number to the n. And then these values of C and n will just be dependent on your Rayleigh number. So in this region from 10 to the 4th to 10 to the 9th, we're going to use 0.59 for the coefficient and 1/4 for the exponent. Plug in these numbers, Nusselt number of 88. Now, right beneath this equation in my table in the Sengel textbook, there's another equation that says it's useful over the entire operating range. So not just over one Rayleigh number, over a bunch of Rayleigh numbers. And so it's way more complex. We'll have to put in the Rayleigh number. We have to put in the Prandtl number. We've got powers of the 9/16th power raised to the 8/27th power. This is a whole lot of fun. Type all this in, give my calculator a real workout here. 96.62 is now the value. So here I have two equations from the same textbook, both within the range of values that says that they're allowed to be used, and I get an answer that's 10% different, even in the same textbook. Now, part of this difference can actually be explained if I go to the Leinhardt textbook, which shows some of the experimental data by Churchill and Chu that this Nusselt number equation, this big one, actually comes from. And in fact, in this textbook, they gave us a third equation that's applicable at Rayleigh numbers less than 10 to the ninth, which we just barely squeak into, right? We just barely fit. This 0.68 plus 0.67, and this is the line that's fit on this graph. And if we plug in the numbers into this equation, now we get a Nusselt number of 77.37. And that's about 20% less than this orange equation version. So we've got one equation that the textbooks both say is useful over the entire range, a really easy equation that's useful only a small range, and then a really complicated equation that's useful over a small range. But all three should be valid, and we get a 20% spread in between them. And if I zoom in on this graph, you might see why this happens. The vertical axis on this graph is logarithmic. So even though it looks like this line is fitting the data pretty well, and then maybe at the right side of the graph, it starts to be a little bit too low, below the line. But keep in mind that being off by just a tiny bit on this graph, this is logarithmic. Each of these two horizontal lines are a factor of 10 apart, right? 10 to the first power is 10, 10 to the second power, 100, 10 to the third power, 1,000. So this small change between the horizontal lines on the graph is actually a factor of 10 apart. It's not just like from 50 to 60, it's from 10 to 100 to 1,000. So being just a tiny bit below the line is very easily, you could see how that would be an error of 20% or even 100% error. So what do we do? So at this point, you just have to choose and justify your choice. So I'm going to go with the orange equation, basically by justifying by saying that the blue equation is just too simple. It really is just the easiest to calculate, but really can't possibly be the most accurate one. And I'm going to say that the green equation is an underestimate because that green line was made for laminar flow and it tracks really well on the left side of the graph, but it's definitely an underestimate on the right side. And even though technically we're within the range where it should be useful, we're right on the edge of the range. So it's probably an underestimate at this range. So I'm going to go ahead and grab the orange value. But if you wanted to do something like average all three of these together, that would probably be fine too. Or even if you just chose the 88 because it's the one in the middle, remember that they're all wrong. So just make a choice and justify it. And if you want to actually just use whichever one happens to be in your textbook, that's probably the one your professor's looking for. So 96.62 times K divided by L gives me an H value of 4.396, which at least is in the realm of expectation for natural convection. You expect natural convection to be small numbers like 2 or 10, right? Forced convection can get way higher than that. Natural convection, 5, something like that. And then plug back into Newton's law of cooling, 47.5 watts. So this is the vertical plate, 47.5 watts emitted by natural convection. So now let's compare that to a horizontal plate with the hot surface facing up versus the hot surface pointing down. I'm going to rewrite my Rayleigh number here and the characteristic length that I already found, just so I don't have to keep scrolling back and forth across the page. Same equation, Newton's law of cooling, HA delta T. The area is still the 0.6 squared. Even though the characteristic length is different, the surface area is still the same. So Nusselt number times K divided by L. And the L, though, in this denominator, this is the characteristic length. So there is 0.15 in the denominator, not 0.6 in the denominator for K over L. So I'll start off with the Sengel table again, the easy version of these equations. For the hot side up, with a Rayleigh number of 7.75 times 10 to the 6, that gets us in the range where we're using 0.54 Rayleigh to the 1/4. And for the hot side down, 0.27 Rayleigh number to the 1/4, so exactly half by flipping it upside down. So we get values of about 28 for the Nusselt number pointing up and 14 for the Nusselt number pointing down. And remember, these Nusselt numbers cannot be directly compared to the Nusselt numbers from the vertical case, because in the vertical case, the characteristic length was different. And so we're going to have to wait to do comparisons until we actually get answers for H or for Q. Those will be directly comparable. But comparing these two against each other, it should be obvious right away that the hot side facing up is going to have better natural convection. And this should make sense because if the hot surface is pointing up, then when the air gets hot, it just goes up, right? Hot air rises, the hot air goes up, and then cold air can very easily kind of sweep in from the side to replace it. And then once it heats up, it just leaves the surface and can be replaced again. When you put the hot side down, when a piece of air in the middle gets heated up, it can't go up, but it doesn't go down either. So what it really has to do is get pushed off to the side. And so what that means is the hot air from the middle kind of occupies the space along the edge so that no cold air can kind of get there quite as easily. So basically all of the hot air from the middle blocks the surfaces around the edge, and that provides an extra layer that the heat has to get through the hot air in order to get to the cold air. It's a lot of extra resistance. So heat transfer is worse when the hot air is facing down because all the hot air is in the way. It doesn't leave the plate very easily. So these first two equations were super easy, but just as before, every textbook is going to have different equations for this. So if I go to the Bergman textbook, for the hot side facing down, I'm going to get 0.52 Rayleigh number to the 1/5 power. And I can plug in some numbers there and get a Nusselt number of 12.4. And okay, 12 to 14, those seem kind of close. That's actually like a 15% error in between those. So that's not really that close. If I look at the hot side facing up, I can go to the Laminar textbook, which again, I normally like the Laminar textbook for equations because it's a brand new book, right? The new edition was just published in 2020. And they're really good at explaining why they're using which version of the equation. Basically, they're really good at calling out old versions of the equations and showing why this is the best version to use. So theirs is 0.56 Rayleigh to the 1/4 divided by a whole bunch of junk in the denominator. Again, 9 to the 16th power. And now their Nusselt number comes out to be 22.66. And this is way lower than the other one, right? This is, 25% lower. So the Laminar textbook also has a different version for hot side down, 0.58 Rayleigh number to the 1/5, which is the exact same form as the Bergman, just with a different coefficient. This gives me a value of 13.84. Is this frustrating to you as much as it is to me, right? I really just want to look up an equation, find the equation, and plug in my numbers. Is that really so much to ask? So let's suppose I want to just grab these two orange equations from the Laminar textbook that I think is most accurate. If I plug in Q dot, my 22.66, K over L, I get Q dot 44.5 watts. And so right off the bat, I'm going to see that this is actually going to cause a problem because for our vertical surface, we got a value of Q dot of 47.5. So we're saying that the hot surface facing up is worse than the vertical surface. And I know that's not true. For the same reason that a horizontal surface is bad with the hot side facing down because the hot air gets in the way along the edge, the same thing happens on the vertical surface. All of the hot air on the bottom of the vertical surface goes up. The hot air rises, it goes up along the vertical surface. So towards the top of the surface then, there's not cold air touching the surface, right? So all of the heat from the surface has to go through the hot air in order to get to the cold air. So you get good heat transfer at the bottom of the wall, but at the top of the wall, your heat transfer is a little bit worse. So as far as heat transfer goes, it should be hot side facing down is the worst, vertical is in the middle, and hot side facing up is the best. And that's because the hot side facing up has the hot air get out of the way the easiest. The hot air gets out of the way next easiest on the vertical, and it's the hardest for the hot air to get out of the way with hot side facing down. So what this kind of means is when I am choosing which equation to use, I need to be consistent in between my three different methods. So when I chose my equation for the vertical wall, I chose an equation from the Sengel textbook, one that was on the higher end of Nusselt number. I didn't use my Lionheart equation, which was on the lower end. So now when I'm looking at my Nusselt numbers here, I need to again use one that's on the higher end so that I'm kind of comparing apples to apples, not apples to oranges. And so let's actually take a look at what Rayleigh number each equations are useful over, and that might give me sort of a clue as to how good or bad a choice they are. So my orange Lionheart equation is useful for a Rayleigh number less than 10 to the 7th. And for this problem, I have 7.75 times 10 to the 6th. So I'm actually just barely within that range. But same for the blue equation. The blue one's only useful 10 to the 4th times 10 to the 7th. So again, I'm kind of barely in that range also. This makes me wonder then, what would the Rayleigh number be if I were above 10 to the 7th? Because I'm right on the border. Maybe I should check what it would be if I were just above. So there I can see an equation 0.15 Rayleigh number to the 1/3, and I get a Nusselt value of 29.68. And so the 28.4 and the 29.6, these numbers are pretty close together, which you would expect right on the border where one stops being good and the other starts being used. And so I'm going to call this orange Nusselt equation that I got from the Lionheart textbook kind of an outlier. And I'm going to use my 28.49 value just because it's going to be more consistent with the equation I used for the other vertical surface. So same kind of analysis for the hot side facing down. I can see that my blue equation is useful for a super wide range to the 5th to the 11th. The 12 value, again, is good right in the middle of the range, 10 to the 4th times 10 to the 9th. And the value from the Lionheart textbook's also kind of in the middle of the range too. So just for, again, to use all the equations from the same textbook, I'll grab this 14 value and just kind of run with it. But realistically, every equation on this page, like, you could really use any one that you want. So plugging these into the Newton's law of cooling, I get a Q dot of 56 watts with the hot side up, 28 watts with the hot side down. Again, and now this is the result that I was expecting. Hot side up should have the highest. Vertical should be a little bit lower, but still pretty good. And hot side down should be much lower. It's a much harder path for the hot air to escape when the hot side is facing down from the horizontal surface. And with that, you are probably ready for a break. There's no way you want to watch another heat transfer video right now. This was a lot to take in. So my heat transfer playlist is up on the screen. Just go ahead and click on it and bookmark it for later. When it comes time to doing another homework assignment or study for your test, you'll be able to just come back to your bookmarks and see my full heat transfer playlist and watch another video later. But right now, take a break. You earned it.